All right, welcome to chapter 18, which is the exact opposite of chapter 17, where we're calculating the molar solubility and K is given. Okay, remember when K is given, you almost always have to use an ice chart, so you can kind of see that down here. So look, identify the major species. Looks like lead to chloride, and I see a KSP value, which is my hint that this is a salt, metal, nonmetal, or ionic, okay, +2, -1, that is not very soluble because I see a KSP value. So I'm going to write out my reaction as my solid salt at equilibrium with its ions. Okay, and my equilibrium expression is going to look something like this. KSP equals products over reactants raised to their coefficients. So my chloride is going to get a 2 up here, and this is a solid, so we do not include solids in our KSP expression, or any equilibrium expression for that matter. All right, so I'm going to set up my ice chart. I'm going to rewrite out the reaction again, PbCl2 in equilibrium, because it is not a very soluble salt with its ions, ICE. All right, so look, we don't care about solids, right? So nothing initially, right? So let x equal something. Let's let it equal the lead so that when we call this x, we have gained x here, and this is 2x instead of having to do fractions. Okay, so 0 and x is x, 0, 2x is 2x. Now we plug these into our expression. So remember KSP is given 8 times 10 to the -5th equals x, and then we have 2x going in for the chloride, and then don't forget about this 2 right here. Okay, so this ends up being 4x squared right here, and then times x. So 8 times 10 to the -5th equals 4x cubed. You divide both sides by 4 and cube root. When you do that, you end up with x equaling 0.03 molar. Remember, these are concentrations, so it's molarity. Okay, and that is for the lead 2+ ion, correct? So look, the lead 2+ ion and the lead 2 chloride are in a 1-to-1 ratio. So if that's how much lead 2+ ion, that's the same number for the lead 2 chloride. So what does this mean? It means you can get 0.03 moles of lead 2 chloride to dissolve in every 1 liter of solution. This is not a lot, so I could have you actually convert this into grams, which I did do, and you would just take moles and turn it into grams using molar mass. I'm gonna have to look up lead 2 chloride. All right, it looks like it's 278.1 grams per mole. So if you take your moles, you end up at 8 grams per liter. What does that mean? That means you can get 8 grams of lead 2 chloride to dissolve in every liter. That is where saturation happens. After 8 grams, you cannot get any more to dissolve. So anything up until 8 grams, you can get to dissolve. Anything after 8 grams per liter will not dissolve. So 8 grams of solid is not a lot for a liter of solution, assuming you know water is going to be our solvent, right? So this is very limited solubility. Only 8 grams per liter will dissolve, which, look at the KSP value. It's a small number, meaning we have mostly reactants at equilibrium. So most of it stays in the solid form and only a little bit of it will ionize. And again, only 8 grams for every liter. So this is molar solubility in moles per liter right here. This one would be solubility in terms of grams per liter, which is just using molar mass to turn moles into grams. And again, it tells us how soluble or insoluble some of these salts are.